All right, let's consider question number 8, which asks us about acetone. And it says acetone is a solvent and as a reactant in the manufacture of some plexiglass. This acetone, it boils at 56.1 degrees Celsius. We want to know what is the boiling point in degrees Fahrenheit. So ultimately what we're going to want to do here is convert a Celsius temperature into a Fahrenheit temperature. And of course, both of the Celsius, Fahrenheit, and even Kelvin scale can measure and report and quantify temperature. But they're just different scales, and there are equations to convert between these. This is outlined on pages 25 through 27 of your textbook, and this is just one example of these types of problems. You could convert between any unit of measure, okay? All right, so first off, we are dealing with a substance called acetone, and you've probably heard that before. That is a nail polish remover if you're one to paint your fingernails. And you can use that as nail polish remover. It's also a pretty common laboratory and industrial solvent. This is the structure of acetone if we were to actually look at it. And remember, when we draw these structures, anytime I put these lines in, those lines represent chemical bonds. And we'll learn later this semester how to draw structures like this if you're not familiar with it already. But this particular molecule has a single bond between carbon atoms, and then each of these carbon atoms, as it turns out, I probably shouldn't draw it like that, but each of these carbon atoms has an additional 3 bonds to hydrogen. This is an H. All 3 of these are H's. So it's CH3 on this end, same group over here, and then in between, in the middle, we've got a carbon with 2 lines, or a double bond to the oxygen. And of course, the double bonds, as you might expect, are a little bit stronger than just a single bond, okay? But that's our acetone. Now this stuff has got this boiling point, 56.1 degrees Celsius. That's what we know about it. And we want to convert that to Fahrenheit degrees. That's going to be our ultimate goal here. All right, so to help us with this, I think we might want to spend a little bit of time familiarizing ourselves or reminding ourselves of these 3 temperature scales that are pretty commonly employed. Now, Fahrenheit, that's the one that we want to go to here, is in our lives these days typically used for like weather forecasting, right? You turn on the news at night, you hear the meteorologists say, oh, tomorrow in Lubbock, it's going to be 104 degrees. And that temperature that they report is in Fahrenheit. Generally speaking, they don't use any other unit than just Fahrenheit. That's what we're used to when we hear our weather reports. But the thing is that chemists, physical scientists, and almost everyone else, other countries, don't really use or embrace that Fahrenheit scale so much. Instead, they use the Celsius scale. Now, both of these scales can tell us about temperature. There's nothing fundamentally wrong with either one. It's just that they're different units of measure. They're not the same, okay? And because of that, they're not necessarily equivalent. Now, to demonstrate the relationship between the different scales of temperature, we can consider the figure that's here in the middle of this slide, okay? And what this figure is actually meant to show, let me see if I can zoom in on it a little bit more. Not sure if I'll be able to or not here. What this figure is there, I can do it. What this figure is meant to show is the relationship between these temperature scales. Okay, now if we look closely at this relationship, we can see that indeed they're not the same. Let me erase this for a second while we talk about this. Now, to help us visualize differences between these scales, what we're going to do is we're going to consider a very common substance, water. And water, as we said earlier, can exist in different phases. It can be liquid, it can be a solid ice, or it can be a gas, right? And we know that just from common experience. Well, the phase transitions for water occur at different temperatures at atmospheric pressure. And since we're talking about temperature here, it might stand to reason that we could use, say, the freezing point of water, where ice transforms from a liquid into a solid, that's the freezing point, or the melting point, vice versa, right, where the ice melts. You can use that normal melting point. It's kind of a common reference scale for all these temperature measurements. And that's actually what's done right here on this slide. So if you're familiar with meteorological temperatures, Fahrenheit temperatures, you may be familiar that the freezing temperature is 32 degrees Fahrenheit. So in the wintertime, here in a few months from now, maybe the meteorologist will come on and say, oh, the temperature should drop below freezing tonight. What the meteorologist is talking about is that temperature. He thinks, or she thinks, the temperature might go below 32 degrees Fahrenheit. That's the freezing point of water. Now, what is the freezing point in other scales? Well, in Celsius, the freezing point for water is 0 degrees Celsius. It's actually very convenient because the 0 in the Celsius scale is defined by water's freezing point. That's where the scale starts. It's our 0, so to speak, when I say starts. You can have negative Celsius temperatures as well, but that's our reference point for 0, okay? So it's really quite simple. Now, what about higher temperatures, okay? Well, think about phase transitions of water. We can certainly heat water up on our stovetop and eventually it boils. And if that experiment's happening at atmospheric pressure, exactly atmospheric pressure, we're going to achieve what's called the normal boiling point of water. The normal boiling point of water is 100 degrees Celsius. So that's kind of convenient. Our Celsius scale is based on the phase transitions of water, isn't it? 0 degrees is where water freezes in Celsius. 100 degrees is where it boils. And all we do is break up the temperature in 100 individual little parts between the freezing point and the boiling point. And that's equivalent to 1 Celsius degree. But in the Fahrenheit scale, 212 Fahrenheit is the boiling point of water. So it's not the same, it's a different scale. Now there's one more scale in the middle that I haven't talked about yet, and this is actually the one that we're going to use the most. It's called the Kelvin scale, although we use Celsius a lot. We hardly never use Fahrenheit though in the lab, okay? We don't use that at all. That's just like for meteorology and weather reports, okay? But the Kelvin scale, we will use. Sometimes we use it exclusively when we get in this class, like when we talk about gas laws and gas behavior later on. And the reason why this Kelvin scale is sometimes used a lot in physical sciences is because that it's an absolute scale of sorts. All right, now let's see what I mean by that. We said that the Celsius scale was based on water, wasn't it? The freezing point and the boiling point of water. The Kelvin scale, it is not based on water. It's more universal than that. We have a little bit of a problem with the Celsius scale. Our 0 point is where water freezes. So I'll pose a hypothetical question to you for a second. Isn't it possible to cool down ice to lower temperatures than the freezing point? I mean, is 0 degrees Celsius the lowest possible temperature that we can ever achieve? And the answer, of course, is no. We can achieve temperatures lower than 0 Celsius or colder than 0 Celsius. So on the Celsius scale, we could just give those negative values, right? -5 Celsius, -15, no big deal, okay? But on a sort of a universal scale or an absolute scale, that's going to be our Kelvin scale in the middle, wouldn't it make more sense to define a 0 point, a 0 reference point that is essentially the lowest possible temperature that could ever be achieved? The lowest possible temperature that could ever be achieved. So way down here on our Kelvin scale, I do just that. I define my 0 degree Kelvin mark, which we call absolute zero. Absolute zero is the name that's given to that. Now we've actually in the lab not ever reached the absolute zero temperature, gotten pretty close, on the order of 10 to the minus 8, 10 to the minus 9 Kelvin has been achieved, so pretty darn close, okay, but we haven't actually got exactly to absolute zero, because at that temperature, it's believed that all molecular atomic motion would cease. The material would have no thermal energy associated with it, okay? That's our 0 degree Kelvin, or absolute zero case. So in the Kelvin scale, we set that reference point as our 0. And because all other materials have higher thermal energy, sure enough, they have positive values of Kelvin temperature. You cannot have a negative value of Kelvin temperature. It doesn't make sense, okay? Because 0 is the lowest you can go. It's absolute 0, right? So then how do we relate Kelvin back to Celsius or Fahrenheit? Well, it just so happens to get to our freezing point of water, the Kelvin temperature has to be equal to 273.15 degrees Kelvin. And you'll want to remember that number, probably commit it to memory, because we're going to be converting between Celsius and Kelvin an awful lot. But that 0 point where water freezes or melts, it's 273.15 Kelvin. And that's just what the temperature corresponds to the freezing point of water. There's nothing special about it. Like in the Celsius scale. In the Celsius scale, that's how we set the whole scale up, but Kelvin, not so much. Now the boiling point in the Kelvin scale of water is 373.15. And notice that the gap between the freezing and the boiling point is 100 degrees Kelvin, or 100 kelvins. That's the same as the gap in Celsius. So the cool thing about this is that 1 degree Celsius, the gap is the same as 1 Kelvin degree. In other words, the magnitude of 1 degree is identical. 1 Celsius degree temperature change is equivalent to 1 Kelvin degree temperature change. But that is not equal to a Fahrenheit degree. This is my not equal sign to a Fahrenheit degree. Fahrenheit degree is different. Okay? It turns out 1 Fahrenheit degree is smaller by about a factor of 5/9. So this then sets up our different temperature scales. Now back to this problem, because I hate to deviate too far from that. I hope that you kind of remember that discussion before from perhaps a previous chemistry class. But we'd like to gain the ability to convert back and forth between these different temperature scales. And this is one example problem of doing so, okay? Now, the equations to do so are all outlined on basically pages 25 through 27 in your textbook. I'm just kind of paging through that, and gosh, it looks like they did a pretty good job of writing down the different equations. They call them 1.2, 1.3, 1.4. And you can use this equation to convert back and forth between Kelvin and Celsius, and then also Fahrenheit and Celsius, which we're going to do here in a second, okay? Well, I guess one equation to commit to memory that's pretty important, is if you want to convert between Kelvin and Celsius, you can use the following equation to do it. All you need to do is take your Celsius degree and add 273.15, which is our offset to 0. So the Kelvin temperature is equal to the Celsius temperature plus 273.15. And the reason why this equation is somewhat simple is because, remember, a Kelvin degree and a Celsius degree have the same magnitude. They just have different 0 point or a different offset, and you have to add that to account for it. Because 273.15 is equivalent to 0 Celsius. Simple as that. So you want to commit that one to memory. We're going to be doing this equation a lot this semester. You're going to want to get real fluid at converting back and forth between Kelvin and Celsius degrees. Fortunately, it's pretty easy, right? It's just some subtraction or addition depending on which way you're going with the algebra, okay? But here, we're going to work a different problem. This one's going to be a lot less common for us, as it turns out, but it involves going from 56.1 degrees Celsius into Fahrenheit degrees. All right, now how in the world can we do that? Well, if we look at the textbook, we can come across the equation, what they call 1.4, which provides us with a formula to convert between Celsius and Fahrenheit. In this case, we're converting 2 degrees Fahrenheit into degrees Fahrenheit. And to do that, what you do is you take your Celsius temperature, multiply it times 9/5, and then add 32. There's another equation if you want to go to Celsius from Fahrenheit. You can practice with that. That one's 1.5. But here we're going to Fahrenheit degrees. So now that we have our equation, it's a pretty simple calculation. We just have to plug and chug, as it's called, right? Plug the values into the equation. Most notably, that's degrees Celsius. And here for acetone, it has a boiling point of 56.1 degrees Celsius. So I plug that in and solve for my Fahrenheit temperature that corresponds to. If you do the math on that, it turns out the Fahrenheit temperature that you got, or you get on your calculator, is 132.98 degrees Fahrenheit, which is, of course, approximately 133 degrees Fahrenheit. And that's going to be our answer here, okay? So we can work the algebra, work the problem, and get the right answer. But the key content here, I think, for this discussion, for this problem, is that we want to know that there are these 3 different temperature scales, and we want to gain fluidity with conversions between them using the type of equation that we did here. This one that's labeled 1.4 in your book, 1.5 in your book. And we also really need to remember always how to convert back and forth between Celsius and Kelvin temperature. And I think we might have one more problem on that here in a second, probably the next problem, which we'll get to, okay? And those are really the key bits of, or the key skills that I think that you want to learn as a result of this video, as a result of this discussion, okay? All right, let's move on.